we studied about PN junction diodes and their types. In this chapter, we will study basics about transistor. In the transistors, we will study both bipolar junction transistor, that is BJT, and unipolar junction transistor, that is FETs. In FETs, there will be JFET and MOS FETs. We will see later that. Bipolar junction transistor BJT is called bipolar. Bipolar means both types of charge carriers take part in conduction. While in unipolar junction transistor, only one type of charge carrier take part in conduction. Only one type of charge carrier will take part in conduction. Now we will see basics of BJT, bipolar junction transistor. Bipolar junction transistor, BJT. In bipolar junction transistor, both type of charge carriers take part in conduction. Next, if both type of charge carriers take part in conduction, then majority and minority both will be there. If majority is take part in conduction, that is good. If minority take part in conduction, the device will be noisy. So BJT is a noisy device as minority carriers take part in conduction, the BJT is noisy device. Next, the input impedance of BJT is very low, or I can say that input impedance of BJT is low. Next, it is commonly used as an amplifier. It is commonly used as an amplifier for amplification of the signals. So these are the important points for bipolar junction transistor, can be asked in the examinations. Now we will see the construction of bipolar junction transistor BJT. A BJT basically consists of three different layers of semiconductors. One is called emitter, they're called base, and last collector. In a bipolar junction transistor, either emitter and collector can be P region or they can be N region. If emitter and collector are P region, then base will be N region, and if emitter and collector are N region, then base will be P region. So a bipolar transistor will be either PNP or NPN transistor. In bipolar junction transistor, this emitter region and this base region both form a PN junction, this junction, which is represented by JE and called as emitter junction or base emitter junction. And this base region and collector region both forms a junction written as JC, and this junction is called collector junction or collector base junction. Now we will discuss the basic operation of BJT and the grouping and areas of the different layers in the BJT. Now we will consider NPN transistor. In NPN transistor, emitter is N-type material and basic operation is that this base emitter junction will be forward biased and this collector base junction will be reverse biased. If this base emitter junction is forward biased, majority charge carriers will take part in conduction, and this P region, which is base region, is a lightly doped region. If it is lightly doped region, then majority charge carriers in this region will be very less. And emitter is highly doped region. If base emitter junction is forward biased, then the majority charge carriers from N-type region will be injected in the base region, and when these charge carriers are injected into the base region, this base region there will be a large number of electrons, and this region also an N-type region, but the concentration of electrons in this base region will be very large as compared to concentration of electron in this region. So we can say that between these two regions there is change in concentration with respect to change in distance, means concentration gradient is created. Concentration gradient is created. If concentration gradient is created, these charge carriers will diffuse from higher concentration to lower concentration, means these charge carriers will reach to the collector. This is the basic operation of BJT, and now we will discuss about the doping and areas of the region of three layers. Now earlier we discussed that basic operation includes the majority charge carriers of emitter region are injected into the base region, and these injected charge carriers will then diffuse towards collector. Now we will discuss about doping of three layers. First, we want to inject the majority charge carriers that are electrons from emitter region to base region. If these charge carriers will be injected into the base region. So emitter region is highly doped in order to inject more number of charge carriers. Now this base region is lightly doped because we are injecting these majority charge carriers into the base region. If base is highly doped, then there will be large number of holes in this base region, and as we are expecting these injected charge carriers to reach to the collector, due to large number of holes in p-type region, there will be large number of recombinations in the base region. So base is lightly doped in order to reduce the recombinations in base region. In order to reduce recombination, we are doping this lightly. And there are some reasons of moderate doping of collector region, but which are not that much important. So we will just say that collector region is moderately doped. Moderately doped. Collector region is moderately doped. If these are the doping of three regions, so we can say that doping of emitter is greater than doping of collector, and doping of collector is greater than doping of base. This is the range of doping for these three regions in the transistor. Now we will discuss about the areas of three regions. There is no particular region for moderate area of emitter region, but yes, there is region for less area, less width of base region. If we are injecting majority charge carriers into the base region, then we should ensure that the concentration of electrons in base region, that is N, and concentration of electron in collector region, as collector is N type region, this will be very large, but as we are injecting electrons into base region, the electron concentration in base region will increase and should be greater than N dash. This we have to ensure. If N is greater than N dash, so we can see that if we move from base to collector with a distance x, there will be change in electron concentration. So concentration gradient will be created. If concentration gradient is created, then only these charge carriers will diffuse to the collector. Now the area of collector region is kept very large. This is kept very large to ensure that the heat generated at this collector junction should be properly dissipated to the surrounding. As this PN junction, when operated, this junction or collector junction is always reverse biased, and for a reverse bias junction its resistance is very high, and also the number of charge carriers that are crossing the collector junction is very large, means at this junction collector current IC is also high. If this current is high and this resistance high, then at this junction the heat generating IC square into R will be very large, and this much heat should be properly dissipated to the surrounding, otherwise the BJT will burn or uh, will be destroyed. So this collector region is kept very large so that the large area of BJT should be in contact of surrounding. We cannot increase the area of a base, because if a base area is increased, then high concentration gradient will not be created. Now we'll see symbols of BJT. This is the symbol for NPN transistor. This is collector terminal, base terminal, and this is emitter terminal. For this transistor, this collector terminal will be N-type region, this base will be P-type region, this emitter will be N-type region. For this transistor, the actual direction of emitter current IE will be in this, and collector current will flow in this direction, while base current will flow in this direction. If we consider this BJT as a junction, then total outgoing current should be equal to total incoming current. According to KCL equation, total outgoing current, that is IE, should be equal to total incoming current, that is IB plus IC. Now this is the symbol for a PNP transistor. In PNP transistor, collector will be P-type region, base will be N-type region, and emitter will be a P-type region. In this PNP transistor, the emitter current IE will flow in this direction, while collector current IC and IP will flow in the output direction. Again, if we consider this transistor as a junction, then total incoming current IE should be total outgoing current IC plus IP. Also, we will define terminal voltages for a NPN transistor. This is collector, base, and emitter. Between this base and emitter terminals, the voltage drop will be denoted by VBE, base to emitter voltage, while the voltage drop between this collector and base terminal will be denoted by VCB, and the voltage drop across these terminals will be denoted by VCE. These are the terminal voltages of BJT. Now we will see the operating regions of transistor BJT. BJT is operated in 4 different operating regions depending on the biasing of emitter junction and collector junction. First operating region is active region. When operated in active region, base emitter junction or emitter junction is forward biased, while collector junction is reverse biased. When BJT is operated in active region, it can be used as an amplifier. So when we want to use a transistor BJT as an amplifier, we will have to use it in active region. Next, saturation region. Now in BJT, if base emitter junction is forward biased and collector base junction is also forward biased, then in this particular biasing, the transistor is said to be operated in saturation region, and when it is used in saturation region, it behaves like an on switch when it is used in switching circuits or switching applications. Number 3, cutoff region. When both the junctions are reverse biased, BJT is said to be operated in cutoff region, and in cutoff region it behaves like an off switch when it is used in switching circuits. So when biased in active region, BJT can be used as an amplifier, and when biased in saturation and cutoff, BJT can be used as a switch. When operated in saturation, it will be on switch, and when operated in cutoff, it will be off switch. Number 4 is reverse active region. Reverse active region. When collector junction is base emitter junction is reverse biased and collector junction is forward biased. If we bias BJT in this particular fashion, when base emitter junction is reverse biased and collector base junction is forward biased, it we can see that it is just like active region, and we have just reversed the biasing of collector junction and emitter junction. And when we reverse the biasing of collector and emitter junction, BJT operates in active region, reverse active region. And when it is used in reverse active region, it cannot be used as an amplifier, means its gain is low. So if we try to operate emitter in place of collector, means if we interchange these two layers of BJT, then BJT cannot be used as an amplifier. It will not provide any gain to the input signal. Now, equation for collector current IC. Collector current is an important current of BJT, and its equation is given by IC is equal to beta into IP plus 1 plus beta into ICPO, where IC is collector current, IP is base current, beta we will discuss later. ICBO is called collector to base reverse saturation current. Collector to base reverse saturation current when emitter is open. So this is the current when emitter terminal is not biased, and for this NPN transistor, if we bias this particular junction in reverse direction, then the current flowing will be ICBO. Emitter is not biased in this particular case. Also, the equation for collector current IC is given by IC is equal to alpha IE plus ICO. Alpha we will discuss later. IE is emitter current, and ICO is called collector reverse saturation current. Collector reverse saturation current, and this ICO is almost equal to ICBO. There is little difference between these two currents, and if in problem this current is given in place of this, we can use ICO in place of ICBO. We will define one more saturation current, that is ICEO. This is the current in BJT when base terminal is kept open and this collector and emitter terminals are biased. In this case, the current flowing in the BJT is called ICEO. This ICEO is called collector to emitter saturation current, collector to emitter. When base is open, and this current ICEO is given by 1 plus beta into ICBO. Also we can write it as ICEO equal to 1 upon 1 minus alpha to ICBO. Both the relations are same. I can write this as 1 upon 1 minus alpha ICBO. Now we will discuss operating modes of BJT. BJT has three operating modes depending on the input and output terminals. First mode we will discuss is common base mode. Common base mode. In common base mode, the input to the BJT is given at the emitter terminal and output is taken at the collector terminal, and base terminal is kept common between input and output. Here input signal is applied and here the amplified version will be taken. So input will be amplified and amplified version can be collected at the collector terminal. In this common base mode, the current in the input terminal is IE and the current in the output terminal is IC. So for this BJT, I can define its current gain. Its current gain is written as alpha and it is output current by input current IC upon IE. IC and IE both are nearly equal, but IC is less than IE. So I can conclude that alpha is nearly equal to 1 but less than 1. This alpha, now we will call it as current gain of common base BJT. Current gain of common base BJT. The second operating mode is Common emitter mode. In common emitter mode, the input signal is applied at the base terminal and output is taken as at collector, while emitter terminal is kept common. Here input is applied and across these two terminals output will be taken. At the input terminal, the current will be base current IB, and at the output terminal the current will be collector current IC. So in common emitter mode we can define current gain, and the current gain in common emitter mode is called beta, and this beta will be output current by input current, and we know that collector current is very greater than base currents, so beta will be very greater than 1, always be greater than 1. Number 3, common collector mode. When it is used in common collector mode, input is applied to the base terminal, output is taken at emitter terminal, while collector terminal is kept common between input and output. In this particular mode, the output current is emitter current IE and the input current is base current IB. We will now define current gain. For this BJT will be gamma, and it will be output current by input current, and gamma is also very greater than 1. Now relation between alpha, beta and gamma. First relation is between alpha and beta is alpha equal to beta upon 1 plus beta. Next, beta equal to alpha upon 1 minus alpha. Number 3, gamma equal to 1 plus beta. And number 4, gamma equal to 1 upon 1 minus alpha. These are the 4 relations between alpha, beta and gamma. Now the next topic is early effect in BJT. It is also called base width modulation. In a BJT, we bias emitter base junction as forward bias NP and BJT. We bias emitter and base terminals. Junction between emitter and base as forward bias. It will be like this, and the base junction will be reverse biased. As base is lightly doped region, the depletion layer will penetrate more into the base region as compared to collector. Also, as emitter base junction is forward biased, the depletion layer width will be very less, and also the emitter is highly doped region, so depletion layer width will be very less. Well, there will be a depletion layer, considerable depletion layer in this region. Now when BJT was fabricated, this was the actual base width, and during operation only this much base width is remain, WB dash, and this is WB. So WB is actual base width and WB dash is effective base width. When we increase this reverse bias voltage is increased, the depletion layer width at this junction will increase, and if depletion layer width is increasing, the effective base width WB dash of transistor decreases. If we decrease this reverse bias voltage, the effect depletion layer width decreases, and if depletion layer width decreases, effective base width, means this width of base WB dash increases. This change in effective base width with this reverse bias voltage is called base width modulation. Is called base width modulation, and particularly this effect when reverse bias voltage increases, WB dash decreases. When reverse bias voltage increases, WB dash decreases. This particular effect is called early effect in BJT. So base width modulation means altering the effective base width with change in reverse bias voltage, and early effect means there is decrease in effective base width when reverse bias voltage increases. This is the base width modulation in BJT. Now we will see some consequences of early effect. Suppose BJT is operating. A basic operation we have already seen that majority charge carriers from emitter will be injected into the base, and these will be uh, diffuse. This will diffuse towards collector region. Now if we decrease the base width, then the number of charge carriers that are in base region, this region, electron, divide by the effective volume of base. This particular ratio, same number of charge carriers are injected into the base region. If we decrease the base volume, then this concentration will increase. If this concentration increases, there will be large concentration gradient between these two regions, because concentration of electron will be very high as compared to concentration of electron in this region, because this region is large. Now if we decrease the effective base width, first effect will be on this concentration gradient will increase, and due to concentration gradient, large number of charge carriers will be reaching to the collector, means collector current IC increases. If collector current IC increases, then the charge carriers that are recombining in this region is in this base region decreases. So due to this, base current IB will decrease, and we know that alpha equal to IC upon IE. If IC increases, alpha increases. And number 4, beta equal to IC upon IB. In BJT, IC increases due to early effect and IB decreases due to early effect, beta increases. Now we will solve some problems on BJT. calculate beta of transistor if its alpha is equal to 0.98. We know that beta is equal to alpha upon 1 minus alpha. It will be 0.98 upon 1 minus 0.98. It will be 40. Next question. Calculate the collector current IC of transistor if base current IP equal to 20 microamperes and common base mode current gain is 0.9. In this question, we are given base current IB equal to 20 microamperes and common base mode current gain means alpha is given, alpha equal to 0.98. If alpha equal to 0.98, we can calculate beta, which will be equal to alpha upon 1 minus alpha will be equal to 49. Now, equation for collector current IC, we know that this equation IC is equal to beta into IB plus 1 plus beta into ICBO. This part ICBO is a reverse saturation current and sometimes it will be given in the problem, and if not given, you can neglect this part from this equation. If we neglect this part, then IC will be nearly equal to beta into IB. If IC is equal to beta into IB, we can calculate by putting beta in IB. Beta is 49 and IB equal to 20 microamperes. It will be 0.98 milliamperes. So the collector current IC for the transistor will be 0.98 milliamperes. Next question. The collector to base reverse saturation current for transistor ICBO equal to 20 microamperes and common emitter mode current gain is 100. Calculate ICEO collector to emitter current when base is open. We know that ICEO for BJT is equal to 1 plus beta into ICBO, and it can also be written as 1 upon 1 minus alpha into ICBO. For this transistor, beta is given as 100, so 1 plus 100 into ICBO will be 20 microamperes. Calculating this, we get ICO equal to 2.02 milliamperes. Now, apart from these topics in BJT, we have some more topics, that is biasing of BJT. There will be problems on biasing. Next, AC analysis. AC analysis of BJT. In the AC analysis, we will have low frequency model and high frequency model. Low frequency and high frequency model of BJT. All these topics will be covered in analog electronics because according to syllabus of GATE, these all these topics come under analog electronics or analog circuits. So this was all about electronic devices and circuits as far as electronic devices and circuits are concerned.